Here we'll take a look at what continuity at the endpoints of an interval might look like and what it might mean for a function to be continuous on a closed interval. So if we had something like a to b and we contained those two endpoints, we said it's continuous on this closed interval. What does that look like? What does that mean? So first we have to give a definition here. It says let a be some interval. So we're just talking about the interval a to b. That's the only thing we're considering right now. A function f is continuous from the right, or it is right continuous at a if the limit as x approaches a from the right of f of x is equal to f of a. And f is continuous from the left, or it is left continuous at b, if the limit as x approaches b from the left-hand side of f of x is equal to f of b. So I think some pictures would help here. Let's say I had a function. Let's say here's my interval. Here's a, here's b. In this case, let's have this function exist right here at a, but maybe I have, maybe I have a hole right here, an open circle there at b. So if I wanted to talk about this function is continuous on the interval a to b, where it is we are including a and not including b. So what that means is that this function is right continuous. It is right continuous, but not left continuous. And the reason here we use those terms, the right and the left, is because if you look at a, when we talk about a right here, we're looking only at the limit from the right-hand side because that's the only part that makes sense. If we're strictly living on this interval right here, a to b, it doesn't make sense for me to talk about the left-hand side of a. It only makes sense for me to talk about the right-hand side of a. So that's why we're using these terms left and right. So if I gave another example, right, so if I switched these two around, if here's a, here's b, perhaps this time I have a hole at a, but my function does exist over here at b, then I would say, okay, this is now continuous on a to b, where a is not included, but b is. In this case, we would say that this function is left continuous at b, but not right continuous. Not right continuous at a. So here I can look at, we're saying it's left continuous at b here because we're only looking at the limit as x approaches b from the left-hand side. Again, we're living on this interval over here from a to b. We don't really care what the right-hand side of b looks like. Maybe it's not relevant to our domain. Maybe those values don't make sense for our problem. In either case, if this is the interval that we're living on, then I don't care about that right-hand side, which is why I need to define this idea of left continuous. And then, of course, if we contain both of our intervals, so let's say if I have, we'll make it really small over here. I'm running out of room. So let's say I have a function that looks like this. If I contain both of my endpoints, then of course this function is continuous on a to b on that closed interval. It is both left and right continuous. It is right continuous at a, and it is left continuous at b. So I want to use this idea here to help me define continuity on an interval here. So we say a function f is continuous on an interval I if it is continuous at all points of that interval I. So if I contains its endpoints, continuity means continuous from the left and the right. So here we're going to use this to help us look at a piecewise defined function. So here I have f of x equals x squared plus 1 if x is less than or equal to 0, and 3x plus 5 if x is greater than 0. So I'm going to look at my two intervals actually to start off. Here I have x is less than or equal to 0 and x is greater than 0. I look at that and I see two intervals here. So I see for x is less than or equal to 0, we're talking about all of the negative numbers, and because it is or equal to 0, right, it's less than or equal to 0, we are including 0. So we're talking about here negative infinity to 0. 0 is included here in this case. And then x is greater than 0. Here we're talking about all of the positive numbers, but this time because it's strictly greater than 0, we're only talking about positive numbers. We are not including 0 in this interval. So we're just going to say 0 to positive infinity here. So essentially what I have here are two intervals. So I'm going to break this up. I'm going to look at how this function is defined on each one of these intervals. So let's start with this top one here. Let's do this in red here. So I'm going to look at x squared plus 1 to start off. So for x squared plus 1, what do I know about x squared plus 1? Well, this is a polynomial. And what do we know about polynomials? Well, polynomials are nice because they are continuous everywhere. I know I'm abbreviating a lot, but they're continuous everywhere, which means it's certainly continuous on negative infinity to 0. So that's cool. This part, boom, we're done. I'll look at this bottom part now. Let's do that in a different color. Let's do that in blue now. So here I'm going to look at 3x plus 5. Again, I'll look at 3x plus 5, and I'll just think about what type of function it is. Well, again, it's a polynomial. What do we know about polynomials? Well, they're continuous everywhere, right? I'm not going to write that whole word out. So it's certainly continuous on its domain, how it's defined, 0 to positive infinity here. So this is good. We've determined that it's continuous on negative infinity to 0 and 0 to infinity. But we need to check something now. We know that it is continuous on these two intervals. And let me get a better color here. It's continuous on these two intervals. So it's either continuous on negative infinity to 0, 0 to infinity. So here we're saying, just to kind of clarify our language here we are saying it is left continuous at 0, but it is not right continuous. It is left continuous, but not right continuous. So that is a possibility. Or it could be both left and right continuous at 0. And if that's the case, we would just say, well, it's continuous on negative infinity to positive infinity. So what we need to do is we need to determine, hey, is this function going to be right continuous at 0? So we may need to go back and look at our definition of right continuous here. So when we talk about right continuous here, remember we're talking about the limit as x approaches a from the right-hand side. Is that equal to f of a? So let's start off with the easier of the two to talk about here. And let me change my color. Let's talk about f of 0 here. F of 0, where do I plug that in? Well, I want to plug that into where it is less than or equal to 0, since 0 is equal to 0. So I plug that into x squared plus 1. 0 squared plus 1 equals 0 plus 1 gives me 1. So there is f of 0. But I now want to determine if we're right continuous at 0, which means I want to look at, well, what's the limit as x approaches 0 from the right-hand side of f of x? But if we're on the right-hand side of 0, and if you need to, you can draw yourself out a little number line, right? Here's my number line, here's 0. If we're approaching from the right-hand side over here, we're talking about positive numbers. We're talking about positive numbers. We're talking about this interval of 0 to positive infinity, which means I'm looking at 3x plus 5. So I'm going to take 0, plug that into 3x plus 5. So I have 3 times 0 plus 5. Which is 0 plus 5 gives me 5. Well, 1 is not equal to 5. So what does that mean for me? That means that this function is not right continuous at x equals 0. It's not right continuous at x equals 0, which means it is not continuous on negative infinity to positive infinity. That means it is continuous on negative infinity to 0, 0 included, and 0 to positive infinity where 0 is not included. It's a very subtle thing, and if you're not familiar with the definition of continuity from the left or continuity from the right, it is easy to mix these two things up. But it's important that we understand the difference between these two, especially for things like piecewise defined functions. I want to look at one more example here in this video, but first we'll talk about this theorem here very quickly. It says assume n is some positive integer. If n is even, then f of x raised to the 1 over nth power is continuous at all points that f is continuous. One thing I want to clarify here when we talk about f of x to the 1 over nth power, another way I can write this, and another way you've probably seen this before, is this really says the nth root of f of x. So you may see it in either form. You may see it given as a rational exponent. You may see it given as a radical. If n is even, then f of x to the 1 over nth power is continuous at all points that f is continuous and f of a is greater than 0. So here we're saying that we need f to be positive. We can't have, say, the square root of a negative number. Essentially, that's what we're worried about here. So what we want to do is we want to look at the index of the root, or the denominator of our power, kind of depending on the notation that we have here, and just try to determine, okay, first of all, is that even or odd? And then if it's even, then we might have a little bit more work to do. So we're going to look at a couple of root functions here just to determine where our function is continuous. So here, let me go back to blue. I have f of x equals square root of 2x plus 5. And you might look at this and say, well, this doesn't really look like either one of these here. When we say square root, really what we really mean is the index of this root. There's really an imaginary 2 there. So another way I could think about this is 2x plus 5 raised to the 1/2 power. So I'm interested in the index of that root, or excuse me, the index of the root, which would be the denominator of our power. So I'm looking at that. I see, okay, it's 2. This is an even root. So what does this mean? It means that so if n is even, then this whole function is continuous at all points where f is continuous. So let's just stop right there and talk about that. 2x plus 5, this is a nice linear function. It's a polynomial. That means it's continuous everywhere. So that's not going to give us any problems. We know that the inside part of this function is continuous everywhere. We also need this function to be greater than or equal to 0 here. So we are mostly interested in here the inside part of that function. So I'm going to take the inside part of this root, which is 2x plus 5. I'm going to take 2x plus 5. I know I can take the square root of positive numbers, so I'm going to say greater than, or 0. I'm going to say that this function is greater than or equal to 0, and I'm going to solve this inequality here, because those are the types of numbers I can take the square root of. I can take the square root of positive numbers and 0. So here we just have a little bit of algebra to do. Here 2x is greater than or equal to negative 5, so x is greater than or equal to negative 5 over 2. Which means that our function here, the function that we began with, the square root of 2x plus 5, this function is continuous wherever x is greater than or equal to negative 5/2. Again, I want to give my answer in interval notation here. That's just what we're going to be using for the vast majority of this class. The sooner we get comfortable with that notation, the better. So x is greater than or equal to negative 5/2. If you need to, draw yourself out a little number line here. So say, okay, Here's my number line. Here's negative 5 halves. The numbers which are greater than negative 5 halves, we're talking about these values over here. So that interval starts at negative 5 halves, and we're going to include that because of the or equal to part here. So negative 5 halves to positive infinity. It is continuous on this particular interval here. Negative 5 halves to positive infinity. So this worked out really, really nicely. Next, I want to do one more here. Here I have h of x equals 4x squared plus x minus 5 to the 4/3 power here. So here, now it's a little bit more clear what the denominator of our power is. We're looking at 3, which is an odd number. So okay, we have 3, this is an odd number, and before I jump into that, you might be still confused about one thing. You might look at that 1 and say, hey, well, that 1 is different than 4. How does that change our problem? And really the short answer is it doesn't, because I can rewrite this if I wanted to. I could rewrite this whole expression, and let me just clean it up here. I could rewrite this whole expression as 4x squared plus x minus 5 to the 4th power, and then raise that to the 1/3 power. There's really not a great reason for you to do this, but you could, and now I see, okay, this is raised to the 1/3 power. Now this looks like 1 over n over here. So in general, the numerator of your fraction of your power is not going to play a big role. You can basically ignore that here. So this is an odd power. So what we're looking at then is we're looking at the inside part. So we had an odd power, and that, actually let me scroll back up here one more time. It's continuous, and let me erase this here. There's a lot going on. We said, okay, it is continuous at all points, that f is continuous. So we just need to check the inside part of our function here, the inside part of our power. So here in this case, we'd be looking at, depending on how you wrote it, 4x squared plus x minus 5, if we're going to ignore that power. So what we can look at this, we can say, okay, well, this is a polynomial. Works out really nicely because polynomials are continuous everywhere. Continuous everywhere. So it must be continuous on negative infinity to positive infinity. This would be my answer. It is continuous everywhere. If you preferred to write it, use blue here. If you prefer to use 4x squared plus x minus 5 to the 4th, all of that raised to the 1/3 power, you can actually look at the same thing. Well, not the same thing, a similar part, right? I can look at this inside part right here. I can look at 4x squared plus x minus 5 to the 4th power and determine that that's a polynomial too. If you wanted to figure out what that is, you'd have to take 4x squared. You'd have to take 4x squared plus x minus 5 times 4x squared plus x minus 5, and you do that 4 times altogether. It'd be a very tedious process, but what you'd end up with is actually still a polynomial. It is still continuous everywhere, which would lead us to the same conclusion, that it is still continuous on negative infinity to positive infinity. So we like odd roots for this reason a little bit better. They just tend to be easier to work with because we don't have to worry about imaginary solutions and things like that.